Picture this scenario. You suddenly get a critical alert. Your user checkout process is taking 5 full seconds. Now, you know as well as I do, 5 seconds in e-commerce, that is an absolute eternity. It is a guaranteed way to lose customers and, more importantly, lose money. Your standard logs are pointing fingers all over the place, but honestly, they are effectively lying to you about where the actual problem is. Well, let's dive into this explainer and solve the mystery of tracing the invisible.
So here is the immediate pain point. You frantically check your Amazon API gateway metrics and, yep, the latency is definitely 5 seconds. You go check your AWS Lambda execution time, and it is also sitting right at exactly 5 seconds. Now, if you stop your investigation right here, you are going to spend hours rewriting your Lambda code, desperately trying to optimize a function that is actually running perfectly fine.
So, why is the API choking? Think about that for a second. The API wasn't actually slow. One hidden dependency was. Because let's face it, in a modern distributed microservices architecture, your code rarely works in isolation. Rewriting that Lambda code is a massive mistake, because the bottleneck? It's somewhere else entirely. Let's walk through this workflow and see how it all connects. Your Lambda function isn't just sitting there computing math in a vacuum, right? It's talking to other services. First, a request hits the API gateway, which triggers your Lambda. Then, Lambda talks to Amazon DynamoDB. It makes an HTTP call out to a third-party payment provider like Stripe, and finally, it drops a message into Amazon SQS. If just one of those downstream services chokes, your entire application grinds to a halt. You simply cannot solve distributed latency by staring at a single server log.
What you actually need is end-to-end visibility. You need AWS X-Ray. To do this, X-Ray relies on one absolutely critical component, and that's the Trace ID. AWS X-Ray is a distributed tracing service that literally follows a single user request from the exact millisecond it hits your front door all the way through every single backend service. It manages this by injecting a unique HTTP header, the Trace ID, right into the request. You can think of it exactly like a digital tracking device slapped onto a package.
As that request moves from your API gateway over to Lambda and down to your database, every single service records what it did, how long it took, and hands that data right back to X-Ray. X-Ray then takes all of those scattered individual data points and stitches them together into 2 incredibly powerful tools, the trace map and the trace details. You literally get a live visual web of your entire architecture. You can watch the requests hop from node to node with the exact latency numbers and error rates hovering right there over the connection lines. It's pretty amazing.
But how does X-Ray actually break down the time spent inside your compute resources? Well, it uses 2 main concepts. The first is the segment. Think of a segment as the overarching record of the compute resource itself. When API Gateway receives the request, it creates a segment. When Lambda takes over, it creates its own segment. The segment essentially raises its hand and says, "Hi, I am the Lambda function, and I ran for 5 seconds." But a segment alone doesn't tell you why it took 5 seconds. For that deeper why, you need the subsegment. Subsegments give you the granular, line-by-line timing details of exactly what your application code was actually doing under the hood. When your Python code pauses to make a database query, the AWS X-Ray SDK wraps that specific action in a subsegment, peeling back the layers to reveal the true hidden timing details beneath the surface. Now look at how the trace details expose the actual truth. You open up the X-Ray console for that failing 5-second checkout. The main Lambda segment, sure, it says 5 seconds, but look right underneath it at the breakdown. The DynamoDB subsegment, just 20 milliseconds. The SQS subsegment, a mere 15 milliseconds. But that external HTTP subsegment calling the Stripe API, 4.9 seconds. Boom. You have instantly isolated the root cause. So, the absolutely crucial point here is that you do not need to rewrite your database queries. You don't need to touch your Lambda execution logic at all. The actual fix required for this system is to just implement a strict timeout or a circuit breaker on your third-party API calls. By seeing the invisible, you just saved yourself hours and hours of completely unnecessary database optimization. Now here's where this gets even more interesting. What if the external API is fast, the database is lightning fast, but the total Lambda duration is still inexplicably slow?
Well, X-Ray actually exposes the exact initialization time of your Lambda execution environment. It physically draws a line right on your trace, visually separating the cold start latency from your actual code execution time. With this, you can definitively prove if your API is just suffering from cold starts rather than bad code.
And on top of that, X-Ray is incredibly smart about how it draws your architecture. Some services, like DynamoDB for instance, don't natively send their own segments to X-Ray. But because your Lambda code generated a subsegment when it made the database call, X-Ray uses that context to automatically draw what's called an inferred segment on your map. It exposes that downstream dependency even if the target service doesn't actively support tracing.
All right, part 1, the trap, finding the exact request.
Now, I really need you to slow down and listen closely to this next part. Out of millions of daily requests, how do you find the one single trace for the specific customer who complained? This is where people mess up, and it is a massive guaranteed trap, especially if you're studying for the AWS DVA-C02 exam. You naturally want to search your traces by a specific user ID or order ID, right? Well, X-Ray allows you to inject this custom business data into your segments, and you have 2 options to do it: annotations and metadata. A developer will very often inject the order ID as metadata. They go to the console, they search for that order ID, and they get absolutely 0 results. Why? Because metadata is completely unindexed. It is literally just extra context stored in the payload. You cannot search it.
To implement this correctly, you must use annotations. Annotations are explicitly indexed by AWS. If you attach that order ID as an annotation instead, you can instantly filter millions of traces to find the exact request that failed for that exact customer during a massive production outage. It is a total game changer.
Moving on to part 2, the performance trap, catastrophic compute overhead. There is one more major pitfall to watch out for here. If you have a high-throughput API handling, say 10,000 requests a second, tracing every single one of those requests is going to result in crushing compute overhead and a frankly catastrophic AWS bill. You don't want that. Instead, you need to configure X-Ray sampling rules. You basically tell X-Ray to record, for example, just the first request every single second, and then only 5% of any additional requests after that. This kind of smart sampling gives you a statistically significant view of your application's health, saving you serious money without crushing your API's performance.
All right, let's lock this down before we finish up today. 3 rapid takeaways to remember. Number 1, AWS X-Ray tracks requests visually across your distributed systems using a unique trace ID. Number 2, segments represent the overall compute resource, while subsegments give you the granular timing to expose those hidden downstream dependencies. And number 3, you absolutely must use annotations, not metadata, to index and search your traces for custom business data.
I want to leave you with this final thought. It's time to stop guessing where your code is failing based on generic server logs. If you aren't tracing your requests end-to-end, you aren't engineering a system, you are just blindly hoping the network behaves. Think about that for a second. If your system went down right now, would your standard logs tell you the truth, or are you just relying on hope? Implement X-Ray, take full control of your architecture, and stop guessing.